Can you take it off?
Okay. Alright, look at that. I got you. We're going to take notes and we're going to do some problems. Alright? We are not doing the lab so that other students can all be here. We can all do the lab on Monday. So, make sure that you have read up on that video analysis lab. Watch the lab on how to plot the points and stuff like that. I even have 3 videos, so you're not going to have to make your own video yet. Eventually we will. But I want you to have some sample videos. I've got my son throwing a ball in some different, vertically. And I think he rolls it up the ramp right there. He's doing some different things. So watch those, and then we'll walk in and we'll analyze all those and then include those in your write-up. So I've called this lesson 2F, the last helpful formula. We've seen several formulas already. I would encourage you to make your own formula chart with a lot of these formulas that aren't on the AP formula chart. Stuff like the definition of velocity. Anybody remember what that is? Change in position over time, or displacement over delta t. Also writing down something, what is delta x? That's final minus initial. What is the definition of acceleration? Some of those other things like that where I was marking, I said, this is useful, but it's not on the formula chart. So today we're talking about the last helpful formula. And our starting point is one of the formulas that we had yesterday. This was midway through. I said, this is a helpful formula. Delta x, the displacement, is v naught delta t plus 1/2 a delta t squared. You can look back in your notes. This was about 2/3 of the way down when we were finding the displacement after looking at the velocity graph. We got to this point right here. So what we're going to do is manipulate this algebraically. It's going to give us something really nice that's going to relate a bunch of different concepts all together. So the first thing we're going to do is multiply everything by 2. So 2 times delta x equals, and then multiply this whole side by 2, and that will get distributed here. So we have 2 v naught delta t, and when I have a 2 times this 1/2, the 1/2 just cancels with the 2, so I have a delta t squared. The next thing that we're going to do is we're going to, so a little star over the side here, we multiply by 2. The next thing we're going to multiply everything by a. So we have 2a delta x equals 2 v naught delta t times a plus this term a delta t squared times a is going to be a squared times delta t squared. So little star note what we did here, we multiplied both sides by a, sort of a running proof here, justification wise. The next thing we're going to remember is that a is equal to delta v over delta t. So in a couple of these places on the right hand side, I'm going to replace a with delta v over delta t. Left hand side I'm going to leave it as is. 2a delta x, but then we've got 2 v naught delta t. I'm going to replace the a with delta v over delta t plus, and I'm going to replace that a squared with delta v squared, I should put it like this, delta v squared over, let's see, delta v squared over delta t squared and that's for the a, and then we still have the times delta t squared. You kind of see maybe why we did that. Go ahead, what's your question?
I'm just saying it's a lot to write down.
It is. But the thing is, if we are able to do this algebraically and symbolically, then we don't have to later on do all this with numbers. We just end up with a nice formula. So here's some of the things that we notice. Delta t's cancel out right there. Delta t squared cancel right there. And for the next step, we're going to remember what delta v is. Delta v is v minus v naught. Anytime you have a delta change, it's just the final minus the initial. So we have 2a delta x equals 2 v naught. That's going to stay the same. This delta v, you with us? V minus v naught plus, replacing this delta v, v minus v naught squared.
Up to the 2v naught, is that a multiplication or minus?
That's a dot, that's a times. Okay? Then we're going to distribute this 2v naught and we're going to expand this term right here. So we have 2a delta x equals 2 v naught v minus 2 v naught squared, because we have 2 v naught times v minus 2 v naught times v naught, so that's v naught squared, plus here we have an a minus b squared, and if you remember, a minus b squared is a squared minus 2ab plus b squared. That's expanding that term right there. So the first term, so b squared minus 2v v naught plus v naught squared. Do y'all remember doing that in your math classes?
Yeah.
Where if you have this right here, then you can multiply it and FOIL it out, turns into a nice, that term right there. Alright, almost finished. So let's see what we have here. 2 v naught v minus 2 v naught v. So those go away completely. Left hand side we still have 2a delta x equals, and if you notice here we have a minus 2 v naught squared and a plus v naught squared. So that's going to be just a minus v naught squared. So minus 2 plus 1, so minus 1. And then plus v squared. That's that term right there. And then I'm going to add v naught squared to both sides. So we have v squared equals v naught squared plus 2a delta x, or as it's usually written, the v squared is over here, v squared equals v naught squared plus 2a delta x. The AP formula chart has this formula on it, but of course they want to emphasize that everything is in one dimension, so they'll put an x right here, so they'll say the final velocity in the x direction is equal to the initial velocity in the x direction plus 2 times the acceleration in the x direction times delta x. That is what you'll find on your AP formula chart. And so just so that we can all make sure that we're on the same page as far as what does this mean, what do each of these terms represent, okay? What is v? Talking about an object's motion, what does v represent? The v, only in this case, this is going to be, this is its final velocity. It's velocity at the end of the time frame, or the time elapsed. So final velocity. Vx naught would be the initial velocity. So we're talking about an object moving during some time frame. It has some acceleration that it has undergone. That's what A represents, the acceleration during that time which has elapsed. And then this is interesting. We don't have any time in this formula, and that's why this formula is helpful, because sometimes you don't know the time. Instead, you know the, not position, displacement. And that's basically what the whole purpose of this formula was, to get rid of the time factor, okay? And to have a useful formula. In normal high school physics classes, they will write this formula like this. They'll say V squared equals, or so they'll say VF for V final equals VI for initial, okay? We're AP, this is college level physics, so we're gonna have the naught, okay, and we're not gonna, we're gonna have the label V, those right there. But then they're gonna say plus 2AD.
For displacement?
Nope, for distance.
Oh.
Because a normal physics class will not differentiate between displacement and distance, okay? That's another way that we are raising our knowledge here. That just because distance traveled is different from displacement, right? I mean, I could start here, walk over here for 10 feet, turn around, walk back to where I started from. What's the distance traveled? 10 plus 10, 20 feet. What's my displacement? 0, okay? And that's going to play a role here. But anyways, just so you know, this is what sometimes other physics classes what they have. All right, I wanted to give you some practice problems for you to kind of see the level of difficulty some of these problems are, and what are all the different things that you have to do. And it turns out that there's a lot, but it's not impossible. So we've got some questions from yesterday. We will finish that later. Let's look at these problems for today. Basically, we're going to work on solving one-dimensional kinematics problems. Okay, and so this is from your book, chapter 2, lesson 6. Okay, where you've got to draw a picture, write down your knowns, write down your unknowns. You've got to sort of use all of your problem-solving techniques in order to solve these. But there's very few problems in life that are really meaningful, that are also have that are really simple, that you just solve in your head. Most things that are worthwhile solving take a little bit. So let's look at that first question. It says a car traveling at 30 meters per second screeches to a halt, leaving 55-meter long skid marks. What was the car's acceleration while braking? We're going to run through the whole thing. I'm going to show you what sort of things that you're going to have to do if you want to successfully solve this problem, problems like this on homework, problems like this on the quiz and test. Okay? One of the first things you want to do is draw a picture. All right? Now, you may be like me, and you're not a great artist. Some of you are really good artists. That's perfect. If you want to draw a car, I'm going to use the dot model, okay, for my car. And I can choose it moving to the left or to the right. It makes the most sense for me for moving right, so I'm just going to have it move right. This says that it's traveling at 30 meters per second, so I'm going to have a little bit of that. So it's traveling for some period of time at 30 meters per second. Then it screeches to a halt, leaving 55-meter long skid marks. So then during from here all the way maybe to the end, it's going to come to a complete stop. So, I need to make that shorter than the 30. So this is where, right here, it's going to start braking. That's probably a few more arrows than we really need. But we get the idea. Its velocity, this is, or its displacement, whichever you want. This, well, I've got these labeled. This is its velocity. So that at this point right here, its velocity is 0 meters per second. So we're just sort of drawing this, filling in what's going on. And it leaves 55 meter long skid marks. That means that from this distance to here, that delta x, or I'm not even going to write, but I'm just going to write little arrows right here. That part right there, that's 55 meters. Okay? What was the car's acceleration while braking? All right? So at this point, we want to go through a normal good process is to write down your knowns and your unknowns. We can spell unknowns. All right? So help me out. What are some of the things that we know? Okay. Velocity. Starting, ooh, I like it. Starting velocity, 30 meters per second. So I'm going to say V naught, 30 meters per second. Somebody else, what's something else that we know?
The displacement.
Okay. We've got something with that 55 meters, and I hear the word displacement thrown around. Yeah, if we consider from right here to right here, then that would be the displacement. Notice we do have to kind of bear in mind that the car was traveling along this time, but we don't have any information about that time period over there. So yeah, we're going to call this our delta x. And you know, this might be a good time, maybe even probably a little before, for us to write a number line on here. Okay? So probably should have done that before, but you know, no harm done. Whoa, that's a really bad line. Let's see if we can fix that up. Or make it a little bit straighter there. Okay. Obviously, I want this to be in the positive direction, that to be in the negative direction. Where do you want to put your origin, or our origin?
The braking.
Where it starts braking? That seems to be a good point. Could we put it over there? Yeah. Could we put it over here? Sure. This does seem like a very logical point for us to start. It's helpful because then if we call this point over here at the very end, you know, that's our final position, x, that's obviously going to be at 55. So our delta x is 55. That tells us what we have just, with our labeling there, we have said that x naught, its starting position, is at 0 meters, and its final position, x, we don't put an F or anything like that, it just is obviously 55 meters. Is there anything else that we know? In the direction, yeah, the arrows are showing that. That's not really much as far as an equation or a value. How to find acceleration? That's a formula. Yep, we're we're on ahead over here. Acceleration would be one of our unknowns. Okay. Now this is where students normally get frustrated because in fact there is one more piece of information, but it's hidden in the problem. And I'll give you a hint. It's about the velocity. We've determined that it's positive, yep, but there's actually a number. Go ahead, what do you got? Here's where the hint is. It is decreasing, but it decreases to a halt, which means 0. When it finally comes to a stop right here, okay, the final velocity is 0 meters per second. That always trips up students. That's the one piece of missing information that's gonna get you. Sometimes if the problem will say, look for that word. If it comes to a halt, boom. If it comes to a stop, you know final velocity. If it says it starts from rest, that's insider physics language for its initial velocity is 0. Okay, so just keep that in mind. That's something that you need to know about. All right, yeah, that seems like all those. There may be more I'm not thinking of, but this is good enough for us. Here's some unknowns. Now we have to do that other process. If you remember, I said a week or two ago. Physics, AP Physics, is more than just here's the formula, here's the things, or or just plug in the numbers. It's all of this stuff combined. We have to now figure out which formula would go well with this. Anybody have a guess? Which formula would be appropriate?
No. Seems really tricky.
Oh, it's on the tip of my tongue. Maybe this formula. Does that kind of look like it'd be helpful for today? Yeah, absolutely. All right, so v squared equals v naught squared plus 2a delta x. And we're obviously need to solve for a. Now, once again, as I mentioned a week or two ago, don't make the mistake of at this point plugging in the numbers and then trying to do all the math. Okay? Instead, solve this equation for your variable. Okay? And then you can just do everything in the calculator, enter. So let's go ahead and do that. So we're going to try to get this a all by itself. I'm going to pull this v naught squared, subtract it from both sides. So v squared minus v naught squared equals 2a delta x, and then divide this side by 2 delta x, this side by 2 delta x. We end up with a is going to be final velocity minus, or squared, minus initial velocity squared over 2 times delta x. And now we can just plug in our numbers, all right? Final velocity is 0 squared. Yes, thank you. Come up here if you need a calculator. Minus 55 squared all over, oh, hold on. Not 55 squared. 30 squared all over 2 times 55. When somebody gets an answer, let me know.
8.18.
I hear 8.18.
I just saw it. If it's wrong,
That's fine. We'll see if anybody else agrees or disagrees.
and that's rounded to the second or third one.
Okay, that's fine. Somebody else have a different answer?
I got it.
Okay, we got that one again. Somebody else.
Negative 8.
I hear a negative 8.18.
Oh yeah, my bad, negative.
Okay, this number is going to be positive, but if you're negative, fine. Okay, I agree with the negative.
My bad.
Now the question is, what are the units going to be?
It's asking for the acceleration.
It is, but we need to make sure that one way that we can check to make sure that our answer is realistic is, well, let's go ahead and do the same thing, but just with the units, all right? So watch this. Velocity is what type of a unit?
Meters per second.
So meters per second squared minus
Meters per second squared.
all over
Meters
2 times meters. Okay? So some number, meters per second squared minus meters per second squared, is going to give us some number of meters per second squared all over meters. Okay? So that would be meters squared over seconds squared times the reciprocal of the denominator, 1 over meters. Those would cancel, and we have meters per second squared. That is the correct. Negative 8.18 seems like a good value. Negative 8.18 meters per second squared. The problem gives us 2 digits, so we probably could round this to 2 digits would probably be appropriate. So maybe 8.2. Yes, question.
And, whenever, like, anytime we're talking about acceleration, it's meters per second squared.
Yes and no. That is the correct standard units. It's always going to be some sort of distance over time squared.
Okay.
You know, like kilometers per
Yeah.
hour squared or something like that. And the reason for that, just real quick, I maybe didn't make a big enough deal about this. Acceleration by definition is a velocity, so a meters per second divided by a time. So that's meters per second times the reciprocal of the denominator, 1 over second, so meters per second squared.
Okay.
Later on next week, we'll talk about objects that are falling due to gravity. The acceleration due to gravity is 9.8 meters per second squared. Okay, so kind of a lot of stuff, all right, but definitely manageable. And honestly, it takes about 5 times as long to do this as a class than it really does on your own. Okay, because you're just like doing all this kind of stuff. All right, let's do another problem here. A bicyclist starts from rest. Should be bells going off in your head there, yep. And accelerates to 4 meters per second squared for 3 seconds. The cyclist then travels for 20 seconds at a constant speed. How far does the cyclist travel? Okay, so still got something going in one dimension, back and forth, left to right. I really like going from left to right, so we're going to have this bicyclist start over here. Starts from rest. I'm going to label that before I forget it. Y'all said it. Initial velocity is 0, so V naught is 0 meters per second. Then he accelerates for 3 seconds, so I'm going to have him going to the right. The cyclist then travels for 20 seconds at a constant speed. So however fast he's going right here, then he's going that same speed the whole rest of the time. So I'm going to put a dot right there. This here, that's 20 seconds. Notice on this problem, they don't give us any distances. They give us the time. Sometimes you just gotta work with what you're given. And this time period right here was 3 seconds. Okay, I'm going to learn from my lesson before, and I'm going to write my number line kind of towards the beginning, okay, of the problem here. So now notice this is time. The 3 seconds and the 20 seconds, that's my timeline, I guess, if you want to think of it like that. Here's going to be my number line. We can choose where positive and negative, it makes no sense that positive is in this direction, negative is in that direction. Where do you want to put the origin?
With the acceleration. Or slows down.
Okay, we can put it right there. The difficulty with that is then we're going to have negative x values at the beginning, okay? Which we can work with, that's not a problem. But I'm going to give you a little bit of experienced advice here. it's going to be a little bit easier for us if we call this 0.
Okay.
No, it's not a bad idea, just a different one.
That's optimistic.
We don't really know what this location is, where he starts coasting, or starts going the same way. We could call it x1 if we wanted to. Maybe it might be better to call it, I don't know, maybe x3. You see, because it's after 3 seconds. I don't know, that's sort of up to us. Do you want to call that x1, or you want to call it x3? I mean, maybe, see, the thing is, if we call this x0, then this could be x1, and in this position over here could be x2. It doesn't mean 2 seconds, it just means the second, but of course we start as kind of 0. All right, we'll do this. This is a little bit more standard. Well, I've seen it both ways. We'll see if this causes us trouble, and if it does, we'll fix it. If not, then we'll just keep going on. All right. Anything else on our picture? We've got the constant speed. I might just remind myself that here he's accelerating, and here he's got a constant speed. What we have here is essentially 2 different scenarios, and it's going to involve 2 different problems, kind of, so to speak, okay? Because I can't talk about his initial velocity and his final velocity, stuff like that, with the whole thing, because he's not accelerating for the whole time. He's only accelerating for this region right here. So we kind of have to treat this like a problem, and then we have to treat this like a problem. Does that make sense? This problem over here is an acceleration problem, and a constant acceleration problem. This over here is a constant velocity problem, okay? So, different things going on. What are the things that we do know?
Initial velocity.
Okay. Initial velocity is 0 meters per second. What else do we know?
Acceleration.
Acceleration in this region right here is 4 meters per second squared. We've got this time frame over here is 3 seconds. So I could put this delta t is 3 seconds, and then maybe over here I could put, for this problem, this delta t is 20 seconds. Does that make sense? What?
Sorry.
Go ahead.
Just a random question.
Nope.
Would it be possible to just label it delta t and then like go subscript or whatever a and then know that it's
Like delta t for section A, delta t for section B?
or acceleration like for a whatever works, like just wondering.
Yeah, you could put whatever notations you want. I think what I'm just going to separate it with a bar here, and I'll do, in fact, I might put the bar a little bit further over here to refer to this whole part over here. So this delta t is 20 seconds. In fact, I might then say, what's the acceleration in this part of the problem? 0. What are some other things that we know?
That is like, are you talking about values?
Yes, values. Or maybe what are some things that are unknown?
Velocity.
Okay, velocity where?
The 20-second interval.
Okay. So, and it's all the same thing right here. What if I call that V1?
Yeah, that's what I call it.
Because that's going to be whatever that, V1, 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 it's going to be that same velocity during that entire time. Okay? What's nice is that V1 is also the final velocity that he hits right there, so I'm going to call that. We don't know what V1 is there either. We do know, because we've determined it, that his starting position is at 0 meters. But we don't know x1. We don't know that position. We don't know x2. Alright? We've got a lot of good stuff here. Let's make sure we don't lose our focus here, lose sight of the forest through the trees. What are they asking us to find?
Distance. The displacement.
Yeah, okay. He said the displacement, how far does the cyclist travel? So that would be from the very beginning all the way to here, right? So find his overall delta x, and we're going to define that as x2 minus x0, which x0 is 0. So basically, if we just figure out what numbers are, is this 30 meters, is it 50 meters? What is this position on the number line?
Repeat the question.
It says how far does he travel? Okay, which is from here all the way to here. Okay, we've determined on our number line that this is the 0 position. So let's say this is the 7. Okay, and let's say this is like 35. So then that would mean that he's traveled 35. Okay, so now we need to look at this and think of some equations that might help us solve. And I'll give you a hint. In this problem, we know a lot more about this section than we know about this section. So let's go ahead and try to figure something out over here. Maybe the velocity or the position, either one. I notice though if I have that velocity it might be kind of helpful. So maybe let's look for an equation that's going to deal with maybe some of those things and velocity. And I'll take some nominations.
Is it x equals x naught plus v naught times t plus 1/2 time acceleration times
AT squared? Possibly. Let's see if we've got all that stuff. Do we have x naught? Do we have v naught? Do we have t? It's been 3 seconds. Do we have the acceleration? Yep. Do we have t? Absolutely, yes. We could use that. We could use that to solve that. Okay. And it's already solved for x. And this is going to, I'll put x1 right there. Yeah, let's do that. Let's give ourselves something here to do. X naught is 0 plus 0 times 3, that's easy, plus 1/2 acceleration, which is 4, and the time is 3 squared. So x1 is 9/36, so 18? Is that 0? That's 0, so 18 meters. Okay, great. We've got a value here. That also kind of is going to give us an idea of what we should be expecting over here. All right, 18 meters. Does that help us? Well, I can add that now to this column over here. X1 is 18 meters. So I know he starts here and he travels for 20 seconds. The problem is, if I'm trying to figure out that distance, okay, I need to know, and all I have is the time. I need to figure out his velocity. Okay, so let's go back and see what's the velocity, what's the final velocity, maybe another equation that's going to help us out here. Dealing with V naught and A and delta T, or T. Let's see if that works. V equals V naught plus AT. do we know the initial velocity? Yep. Do we know the acceleration? Do we know the time that it accelerates? Yeah. We can find the final velocity during that first 3-second time period. So final velocity is, what's the initial velocity? 0. Acceleration?
4.
Time? Yeah, in fact, watch this. 3 meters per second squared times 3 seconds. So one of those cancel, and we end up with the final velocity is 12 meters per second. So when this bicyclist stops accelerating, he's going at 12 meters per second. And actually, I now have that over here, 12 meters per second. So we know he's going 12 meters per second, 12 meters per second, 12 meters per second, 12 meters per second, for 20 seconds. Okay? Any formula that we know that's going to deal with that? V times 20? Yeah, basically. That's the formula delta x equals v delta t. That's one of those, it's not on the formula chart, but it originates from the definition of velocity, delta x over delta t. Or, this is distance equals rate times time, if you remember thinking it like that. So, delta x, this is, let me pause real quick. This is why I said it's good to make your own formula chart, of other helpful formulas, okay? So our velocity, 12 meters per second. Our time, 20 seconds. Now look at this, watch these units. Cancel. Delta x is 240 meters. It's important to note that that right there is from this point all the way to here is, this delta x is 240 meters. So I'm going to have to add that to the 18. So I'm just going to stretch this over here. So our final answer is going to be 18 meters plus 240 meters, total of 258 meters. This is one of the hardest type of problems that you're going to have to deal with. It's a multi-part, multi-step, this deals with this, that deals with that. We use practically every equation in our arsenal. My way of thinking is, if I show you one of the hardest ones, okay, with different parts in it, okay, all the stuff that you could possibly do, when you have the homework problems and you only have something that's like this, or you only have something like that, then you'll be able to handle it, okay? We're going to do our lab on Monday, and so you need to make sure you have that read totally up. Tuesday we'll do a few more problems like this, and then we'll move on to free fall. All right? Thanks.
Mr. Doctor,
Yes.
could I just staple my correction?